Have you ever tried to balance a turbine rotor? In my previous video, I machined this turbine disc in INCONEL. This time, I thought balancing it would be straightforward. I was completely wrong. In this video, I'll show you the mistakes, the redesigns, and finally how I managed to balance this rotor down to just a few milligrams. Hi guys, I'm Alfonso. I've worked as an engineer in the space industry for more than 40 years, and now I share my passion for CNC machining, DIY engineering, and RC turbine development here on the channel. The first step is static balancing of the rotor. I designed and 3D printed a simple balancing device using magnets to support the shaft and a small ball to minimize friction. The first surprise was that the rotor alone was not perfectly balanced, even though it was turned between centers on the lathe. After some investigation, I discovered the real cause. The threads on both ends of the rotor were not symmetric. Even half a turn difference is enough to introduce imbalance at this level. Using this very low friction setup, I carefully ground the rotor until it was perfectly balanced. Then I integrated the turbine disc and repeated the process several times, correcting both the rotor and the disc until the entire assembly was statically balanced. The next step is dynamic balancing. I used a low-cost ADXL 335 accelerometer and an A3144 Hall sensor to detect angular position. I designed and printed several flexible supports and used a brushless motor with a rubber pulley to spin the rotor. But very quickly, I ran into serious problems. The measurements were unstable, resonances appeared everywhere, and vibration was being transmitted directly to the support structure. No matter how many versions I printed, the behavior was always the same. At this point, I realized the design concept itself was wrong. So I switched to a more standard solution, where vibration is isolated from the shaft before reaching the structure. All parts are 3D printed, and I used a 6000 bearing simply because I had many spares. Smaller bearings would also work perfectly here. Because the accelerometer and the Hall sensor come from different systems, I first needed to calibrate the angular offset between them. By adding a significant mass and measuring the phase shift between the Hall signal and vibration peak, I could determine the correct offset. I repeat this at different speeds. Now I removed the added mass and I measured the real rotor imbalance. I used the offset to correct the imbalance position. The oscilloscope was now the limiting factor. To improve accuracy and filtering, I moved to an ESP32. I had no prior experience with this board, but within a couple of hours I had a simple program running in the Arduino IDE. The program reads the Hall sensor, the accelerometer, applies a simple low-pass filter, and plots everything in real time. With this setup, I could measure and correct imbalance with much higher resolution. The final limit was about 2 bits of the filtered signal. At 4,000 revolutions per minute, this corresponds to roughly 1 milligram of imbalance. My conclusion is that building a precise balancing device is not as complex as it may seem. Using an ESP32 and a very simple program, it's possible to reach milligram level accuracy, which is more than enough for RC turbine applications. If you found this video useful, please give it a like and subscribe so you don't miss what's coming next. Thanks for watching and see you in the next one.